So today we'll be going over static equilibrium. So first off, what exactly is equilibrium? Well, this goes back to Newton's first law. So when an object is at rest, it tends to stay at rest, and when an object is in motion, it tends to stay in motion. Now we could actually mathematically represent this as the sum of forces on a body or a particle is equal to zero. This is what equilibrium is. So if let's go ahead and write the Newton's second law here. So the sum of forces acting on a body is equal to the mass of that object times its acceleration. But acceleration could be written another way. Mass times the rate of change of velocity with respect to time. Now we could simplify this a little bit further and say the change of velocity is v2, take away v1, and you could also write this as t2, take away t1 as well. So now when an object, so going back to equilibrium, Newton's first law, an object in motion tends to stay in motion. So when it comes to equilibrium, either the object is at rest or it's moving with constant velocity, which will meet Newton's first law. The sum of forces acting on a body is equal to zero for equilibrium. So let's take the example of an object in motion tends to stay in motion. So whenever there's an object with constant velocity, you have v2 is equal to v1. So this will cancel out and you'll get zero. So the sum of forces at the end of the day will be zero. So this is one example that takes us back to Newton's first law. The sum of forces is equal to zero when a object is moving at constant velocity. Now the other one is when the object is at rest. So in other words, there is absolutely no acceleration, no velocity. So the acceleration or the change in velocity as well is going to be zero. So it takes us back to Newton's first law. And this is what equilibrium is. Now, when it comes specifically stating static equilibrium, this has to do with an object at rest. So it has no acceleration, no velocity. Um, right? The other case was that the object was with constant velocity, but that's not what we're dealing with when it comes to these particular problems. We're dealing with static equilibrium, meaning the object is stationary, is at rest, it has no velocity, no acceleration, and so forth. So now let's go ahead and do some examples. So for this problem, we have here a 10 kilogram cylinder hanged from cable. We have the cable here, and we have cable CA and CB. So these points are basically our restraints here, and these are the cables. Now, when it comes to specifically cables, cables will always be in tension and they cannot be compressed. So in this case, the forces in the cables we refer to as the tension. So this problem statement gave us the cable CB here is subjected to a tension twice of the cable CA. Now we're supposed to find what is the angle theta here for static equilibrium, as well as finding the tension in cable CB and the tension in cable CA. In other words, how much force or tension is going through that cable specifically. Now, the first step here is to draw the free body diagram. So in this case, we're dealing with the object of a 10 kilogram cylinder. So let's go ahead and redraw it. A free body diagram is nothing more than redrawing the object and then just drawing the forces instead of drawing the cables, the ropes, the anything else that's attached to the system. In this way, we represent the object and forces only. That's what a free body diagram is. So I went ahead and drew the cylinder here. Now from the center of mass, I'm drawing an arrow downwards, which is the weight of that cylinder. And then we see that we have a cable attached. So in this case, since we're dealing with objects at rest, this object is not moving. In other words, there's a force equal and opposite to that going through that cable, and it's going to be equal to W here. So now the question is, what is this tension? So since we know this tension has to be equal and opposite to the weight here for static equilibrium, right? So the object stays stationary And we know the weight is equal to the mass times the gravity. So it's nothing more than plugging in numbers here. We have 10 kilograms times 9.81 meters per second squared, which gives us a weight of 98.1 newtons. So we know that this tension has the same force equal and opposite of that for to have static equilibrium. So we know the tension here. So FBD stands for free body diagram if I didn't mention previously. So why did we need this tension here? Well, because since we're going to be dealing with cable CA and CB, we need to know what force is acting downwards along this ring that we see here. What are the forces being applied so we could determine the tensions in either or. Now this is the tension in this cable going down. So initially we first drew the free body diagram on this cylinder, get the tension on this cable going up. Now we're going to be doing a free body diagram on this ring here and just draw the forces being applied to the ring. So let's go ahead and do that. So now we're looking at the ring. In this case, we're not drawing the cables, we're drawing the forces or the tension in those cables. So this one's going to be tension CB because it's cable CB, and this is going to be tension CA because it's cable CA. Now the force going downward here is 98.1 newtons. Now, one thing that may be a little bit confusing, at least it was when I was initially learning this concept, is when we first did the free body diagram on the cylinder here, we had this tension going upward, right? T is equal to 98.1 going upward. But now when we're going it with respect to drawing it, the free body diagram with respect to the ring, we're pointing it downwards. That's because for every action, there's an equal and opposite reaction. So in other words, look at it this way. When you're looking at it from the perspective of the cylinder, the forces have to balance. So the weight is going downward and the tension within that cable is upward because it's holding it up. But when you're looking at it from the perspective of the ring, it's holding down the cylinder. It's holding up the weight. So this ring is being basically kind of dragged downwards with that weight, if that makes sense. Hopefully that brings some clarity. If not, sooner or later you'll understand this concept. But if you look from the perspective of the ring, it's being basically held down by the cylinder, which is why we're drawing it downwards. So it's all about perspective in this case. Let's put it that way. So we're drawing the tensions in all the cables. We have 98.1 going up. We have the tension cable CB and tension cable CA. Now, another thing that was given in the problem statement was essentially that the tension in cable CB is equal to twice that of the tension in cable CA. So keep that in mind in the problem statement. When it comes to these word problems, you have to read carefully. And it did state that the cable CB is subjected to a tension that is twice that of cable CA. So 2 times the tension of CA is equal to the tension of CB. So we could write it in either this way or this way. Now we have all the forces here. We have the ring. Now, when it comes to the ring itself, it's also in static equilibrium, right? It's not in motion, it's at rest. So what that means is the sum of forces along the x direction must be equal to 0 because it's not moving left or right along the x direction, as well as the sum of forces along the y direction is also equal to 0 because it's not moving up or down. It's a stationary object. So now let's go ahead and sum up all the forces in the x and y directions and see what we have and go from there. So now when it comes to the summation of forces along the x direction, here I'm choosing my sign convention. Going to the right is positive. So let's go ahead and get all the forces along the x direction. So we have 2 times tension CA here times cosine theta because we only want the x component of the tension. So in this case, notice that I used the tension CA 2 times CA instead of using the tension CB here, because if I use CB, then we will have more unknowns in this equation. But since we have CA, later on we'll be able to factor the tension along CA out in this equation. So this is equal to 0, right? For static equilibrium along the x, those are the only forces along the horizontal, the x direction, and it's equal to 0. Now let's go ahead and do the sum of forces along the y. So when it comes to the sign convention, I chose up being positive. So we have 2 times tension in cable CA times sine theta plus tension in cable CA times sine 30 degrees. Take away 98.1, since it's going downward, is equal to 0 for static equilibrium. So notice here now we have two equations here. We have this one and we have this one. And what are our unknowns here? Well, we have TCA, that's one unknown. The other unknown is theta. So we have two equations and we have two unknown variables for these equations. That means we're able to solve them. If we have two equations and we have two unknowns, we're able to solve for these unknown variables. So this is where we go ahead and solve for one equation. We could either solve for the tension along cable CA or the angle theta. And then once we solve for that, we plug it into the other equation. So let's go ahead and do that. So let's go ahead and rewrite the sum of forces along the x direction here. So let's go ahead and rewrite this, and we could switch the negative one to the other side of the equation by adding it to both sides of this equation. And we finally get 2 times TCA cosine theta is equal to TCA cosine 30. Since we have TCA on both sides, they end up canceling out. Or you could just divide it to both sides of the equation, and of course it'll still cancel out. So then we're left with, we have 2 cosine theta is equal to cosine 30 degrees, and then we just divide both sides of the equation by 2. So we have it divided by 2, and then we do the cosine inverse to solve for the theta. So theta is equal to cosine inverse cosine 30 divided by 2, which ends up being 64.34 degrees. So this is our theta. Now that we have theta, we're able to go to the other equation, which was the sum of forces in the y direction. So now let's go ahead and do the summation of forces along the y direction. So now that we have theta here, we're able to plug it into this equation. And now the only unknown here would be the TCAs here. So let's go ahead and solve for that. So we have 2 TCA sine 64.34 plus TCA sine 30 is equal to 91.8. From here, you can actually factor out the TCA. So let's go ahead and do that. So now after you factor out the TCA, this is what you get. And you divide both sides of the equation by this in the parentheses 2 sine and so forth. So this cancels with this, of course, and now your tension is equal to 98.1 divided by that. So now TCA is equal to, so the tension in cable CA is equal to 42.6 newtons. Now remember, the tension in cable CB is equal to 2 times CA, which essentially is 85.2 newtons. So there's the first. This is how, using the static equilibrium sum of forces in the x and y being equal to 0, doing your free body diagrams to solve in this case, the tensions in the cables. And these are your answers. You have the angle 64.34. And you have the tensions in cable CA being 42.6, and the tension cable CB being 85.2. So let's go ahead and do another example here. Here for the problem statement, we have springs. So these here drawn are springs, right? So springs BA and BC each have a stiffness or a spring constant K of 500 newtons per meter. And each spring, it has an unstretched length of 3 meters. So the springs at rest are 3 meters in length. Now we're supposed to determine the horizontal force F here applied such that the displacement D here is equal to 1.5 meters. So remember when it comes to springs, the force in the spring is equal to the spring constant K times the X. In this case, X is the displacement or how much the spring is stretched by. So it doesn't count the whole length, only the amount it actually was displaced or stretched. So whether you're compressing the spring or stretching it, it's going to react equal and opposite to the force that's being applied. So in this case, let's go ahead and draw a free body diagram to simplify things a little bit more. So starting off at point B, so we're going to be solving for the force applied. Now, if we think about when it comes to the springs themselves, for every action, there's an equal and opposite reaction. And if you're pulling on the springs, that means they're basically going to be resisting that force. So it's going to be equal and opposite. So it's going to be the opposite way, the direction of each force of the spring. So let's call the force BC and force BA here. So basically, what exactly are these forces of the springs? Well, it's a little bit better in this case since we have the geometry. Let's go ahead and just draw the dimensions of it. So just simplifying a bit, just drawing the sides here instead of drawing the springs itself, we know that this dimension from here all the way to the bottom here is about 6 meters, right? And another dimension given was actually here. D is equal to 1.5 meters. So we have this dimension here, and it's safe to assume that this is right in the middle of the 6 meters. So if we just want to take into account this triangle here, this would be 3 meters. The same goes for the bottom triangle. We would actually be able to solve for the length here, the length L of the spring once we have that force being applied. Remember, D is equal to 1.5 because there is a force pulling on it here. So now just based off trig here, the length of the springs of each spring, since we're dealing with a geometry that's so the length here of this spring is also the same of this length here, so it's the same. So let's go ahead and solve for it. So in this case, we're going to use Pythagorean theorem. L squared is equal to 1.5 squared plus 3 squared. So now square rooting it, we get our length of 3.354 meters. So this is the total length of each spring after it's been stretched. So now in this case, the question is, how much has it been displaced? Well, of course, we just get the actual stretched length, 3.354, take away the original length, 3. So it's been displaced only by 0.354 meters. So this is our x here. So now the question is, what is the force being exerted by the spring BC and BA? Well, going back to our spring equation, the force of a spring is equal to the spring constant K times X. So we have 500 newtons per meter times 0.354 meters. So the meters cancels out, and the forces in the spring is 177 newtons. So that means this is the force in spring BA as well as the force in spring BC. So now we have the forces here, 177 newtons, and we also have 177 the same. So now it's nothing more than static equilibrium. So the summation of forces along the x direction is equal to 0. The summation of forces along the y direction is equal to 0 again. And then you're able to solve for the force F. So now when it comes to the angles, because you need to know the angles so you're able to basically get the x and y component of each of these force vectors along the springs. So you're able to either utilize trig here to find your angle, or you could basically use your slope, your rise, run, and slope. So let's go ahead and draw it out. So this one, basically I'm just drawing the triangle here. So this one is 3 meters, and D is 1.5 meters. And this is the slope here, which basically is the length of the spring. Now, the reason I'm doing this here is because instead of solving for the angle, sine, cosine, you're just able to use the basically similar triangle concept. So just to give you a better idea, SOHCAHTOA, right? SOHCAHTOA, sine theta is equal to opposite over hypotenuse. So instead of going with the opposite over hypotenuse, doing the sine inverse to solve for the sine theta, instead of using sine theta, you basically could just use this ratio here, which is exactly what I'm drawing out. So we have the rise here 3 and we have the run 1.5. We could also draw in the slope of this triangle, but just to simplify it, in this case, let's say saying the sine of this angle here. So drawing it out here, it's getting a little bit messy. So drawing out the angle here. So let's say gain the x component of the force BC. The x component is equal to cosine, which is adjacent over hypotenuse, sine over hypotenuse. So cosine theta, this angle theta, is equal to adjacent over hypotenuse. So 1.5 over the hypotenuse, which was 3.354. So instead of going ahead and doing more steps to solve for the angle theta, I just basically use the fraction adjacent over hypotenuse, 1.5 over 3.345 times the 177 newtons to get your answer. So let's do that again below. So the force in cable in spring BC along the x direction is equal to 177 newtons times cosine theta, which essentially is adjacent over your hypotenuse, 3.354. So instead of writing cosine theta, solving for theta first, then you basically just skip a step here and it makes it a lot faster. So we get 79.16 newtons along the x direction. Now, for whatever reason, if this is a little bit confusing, then by all means, go ahead and solve for your angle theta and just use sine and cosines as you've always done. Little by little, with more practice, this may become a little bit more clearer, more easier to do. So this is for your x direction. Let's go ahead and do the y. So f BC along the y direction is equal to 177. This case is going to be sine theta, which is opposite over hypotenuse. So opposite over 3.354, which is 158.32 newtons. So this is for the spring BC for the x and the y direction. But since the geometry is the same for BA, the spring BA is also going to have the same force along the x direction, 79.16, and the same force along the y direction, 158.32. Now you could go ahead and just do the calculations yourself just to check it. But now we're going to do the sum of forces along the x, along the y, and basically solve for our force F here. So one thing to note just by visual inspection of the forces here in this free body diagram, we see when it comes to the spring forces, the spring BC is basically you have a force going downward along the y direction, and spring BA has a force going upward along the y. And since we know that they're both equal and opposite, just based on similar geometry, then we know along the y direction these two forces cancel out, and the force that we're trying to solve F is only along the x direction. So let's go ahead and skip that step, but you're more than welcome to practice and do the sum of forces along the y direction. So the sum of forces along the x direction is equal to 0 for static equilibrium, and I'm using my sign convention going right to be positive. So in this case, our force F here, being our unknown, is negative F plus, so FBC is 79.16, so 79.16 9.16 newtons. And then the other cable, BA, is the same, 79.16 is equal to 0. So now solving for F, you could go ahead and add F to both sides, take it to the other side. Now our force F, finally, what we're trying to solve for is 158.32 newtons. This is the force that is needed so that in our problem statement, D was given as 1.5 meters. So this is how you solve these problems when it comes to static equilibrium, which you utilize free body diagrams to draw the necessary forces. You usually have to deal with geometry to get either the angles or the lengths. In this case, we had to solve for the stretched length of the spring so we could get the forces that are being exerted on point B such that we're able to use the sum of forces along the x direction and as well as along the y direction to finally solve for the unknown force F here, which finally is 158.32. So this is when it comes to systems in equilibrium, more specifically static equilibrium, where there is no motion, the sum of forces along the x and y direction will be equal to 0.